Welcome again, and what we will do now is try to get the eigenvalues of the Schrodinger equation, which we have written in the form that I am showing here, which is 1 plus V naught sigma over n k E n k minus E equal to 0. So, let me assume discrete states and a single band. So, what we know is, we know E of k, which is E naught, E1, etc., En. So, these are the band states, 1D band states, we know those things, and we know E naught, V naught rather. So, once we know those things, then what we can do is we can plot, we can rewrite the equation as V naught sigma over R 1 upon ER minus E is equal to minus 1. So, we can plot the left hand side as a function of E, so if we do that, what we will get is the following. You see that whenever E is large negative, then we will have the form is such that it will start from some this thing 1 by E from a very large negative value, come down to minus infinity when it approaches ER. So, what we have is the following, that is, let me write down here. This is the energy, and let me say that I have E0 somewhere here. Okay, so let me mark it instead of writing down. So, I have E0, E1, E2, E3, E4, E5, E6, E7, let us say. Okay. So, now I start from a very large negative value. Okay. When I start from a very large negative value, then it goes like this. Okay. And then when I cross this singularity, it changes sign and goes to plus infinity, and when it approaches the next one, comes like that. And then again the same way, when it jumps again, changes sign, comes down here, jumps, changes sign and comes down here, then jumps, changes sign, then if this is the highest eigenvalue, it changes sign and stays that way, positive. Okay. And then we have V naught, the right hand side is just this quantity. Okay. So, just this plot. So, that is minus 1. This is minus 1, and so the points of intersection will give you the energy levels, okay, because that is one of the ways of solving these equations, is graphical ways of solving equation. So, the energy eigenvalues now will correspond to this one, this one, what we see is that there is a slight change in the eigenvalue from the original one, which was at these red pillars, pegs, and then it moves a little bit away from there, and then you see that curve goes away to asymptotically to 0 on this side and asymptotically to 0 on the other side, and this is a split off state, split off energy level. So all these energy levels have changed a little bit, but this one is actually split off, and the split off state, if we compute the eigenstate of the split off level, we will find it localized. Localized near the impurity side. And the wave function around that point will fall off exponentially, and the wave function falls off exponentially. This is one of the states. Supposing it was a repulsive potential. If the potential was repulsive, you will see the split off state at the other end. The split off state will be close to the bottom top of the band, will be near the top of the band. So what we learn from this is that when you have a single impurity, you have a localized split off state, and all the other states of the Hamiltonian are perturbed only very little, only marginally, and that is an interesting result. We will have occasion to think of large number of impurities or disordered systems. We will talk about that sometime in the future. We will now consider a slightly different problem and do a very interesting analysis, and the problem that we are going to consider is a point impurity at the center of a metallic sphere. Of radius, let us say r, capital R. So what I am looking at is a sphere. I have an impurity here, and the radius of this one is r, and I want to know what happens to the distribution of the electrons around the impurity because of interaction with the scattering by the impurity. That is, the conduction electrons are getting scattered by the impurity, and I want to see what happens to the charge density because of the scattering. So because I am dealing with a metal, what I can do is I can use a free electron eigenstates and because I am dealing with a spherical impurity and a spherical potential, okay, spherical potential due to the impurity, we can resort to a partial wave analysis. In the absence of the impurity, the Hamiltonian is just simply minus h cross squared by 2m del square, and the eigenvalue problem is this times psi is equal to E psi. We can solve for this in spherical polar coordinates. We can solve for psi in spherical polar coordinates. We had done that while discussing the augmented plane wave method and the Green's function method. So, it is nothing new. So, if we do that, then I can actually write down psi KLM of R, I can write down as the spherical Bessel function JL K of R times PL modulus M cosine theta e to the power I m phi. Now, with JLKR, because I am having a it is the metal is in a spherical shape, I will also have a normalization constant. So, if I use a normalized wave function, then it will be 1 upon root 2 pi r JL KR PL modulus M cosine theta e to the I m phi. Now, JL KFR has following asymptotic form, that is, I can write down it far away from the impurity site. JL KR actually behaves like 1 upon KR sine. First, let me show you what the asymptotic form of JL KR in the absence of any impurity. So, all I have is sine KR minus L pi by 2. Okay. So, this is the asymptotic form of the spherical Bessel function, and the values of k are determined by because the wave function has to vanish on the surface of the sphere, the wave function vanishes on the surface of the sphere. We have sine KR L pi by 2 should be equal to 0, or we have the condition on k that KR minus L pi by 2 is equal to some n. Okay. So, is equal to n pi, n is an integer. So, depending upon the value of n, kn will be different. So, I can actually write down kn to be pi by r times n plus L by 2. So, this is what happens to a free electron inside a sphere. Now, when I have an impurity, the Hamiltonian is minus h cross squared by 2m del squared. Because it is a spherical potential due to the impurity, it only depends upon V of r. Psi of r is equal to E psi of r. Now, because Vr is spherical, the perturbation is spherical. So, actually I can remove the vector notation on r. Is spherical, we have the angular part theta phi is just ylm theta e to the ylm theta comma phi is equal to plm cosine theta e to the im phi as before. But what happens to the radial part? The radial part will undergo will have a phase shift. So, we can now write down psi k LMR as some r L of r times P Lm cosine theta e to the Im phi, and RL k of r will have the form almost like before, but phase shifted. That will be 1 by r sine kr minus L pi by 2 plus eta L or delta L. Let me call it as delta L. So, delta L is a phase shift. So, this is the standard partial wave analysis of scattering by a spherical potential, and the allowed values now have to satisfy the following, that is KNR plus delta L must be equal to L pi by 2 or minus L pi by 2 is equal to some n pi, or I have KNR plus delta L is equal to pi times n plus L by 2. So, what I have is a term which is the a phase shift of the wave. This depends upon Kn. My new solution will be like will just be phase shifted spherical Bessel's functions in the large R limit. Now, let us see how these allowed values of KNR plus delta L K in this condition, how this compares with the other condition, the condition which was this one. So, I can actually write it as Kn plus delta L Kn by R equal to pi by R n plus L by 2. Now, let us see what happens when we had no impurity. When we had no impurity, if I am looking at just the one dimensional problem, then I have the phase shifts for delta L for different values of k are given by the not the phase shifts, the Kn values are given by K1, K2 etc., all the way up to the Fermi level Kf, and distance between two allowed k points is actually pi by r. So, this is what we see from here. So, because n is an integer, in going from one to the other, now not in this case, but in the case of a free electron, we have pi by r is the difference. Now, what happens when I have a impurity? When I have an impurity, then these points will shift somewhat, in the sense that the new ones are going to be somewhere here for K1, let us say. For K2 it may be somewhere here, for K3 it may be somewhere here, for K4 it may be here, and again for K near Kf it may be this. So, this one is eta L1 and this is eta L Kf. So, what it means is the following: we have not used the entire length of the k from K1 to Kf to for having the states. That means the k vectors of the states that we have used cumulatively, they are smaller than the interval K1 Kf. Okay. So, what it actually means is the following: this implies that we have extra states given by delta K1 minus delta Kf divided by phi so these many extra states that I have, okay, because we have actually we have not this thing used up the entire length, but we have some spare thing that is left out, which I can show you as this part. So this is this part eta L kf minus eta L k1 is the one that is left out, and the number of states that you have are corresponding to that are just given by delta k1 minus delta kf by pi. Now what we know is that a metal has constant Fermi energy throughout the sample at equilibrium. Okay, so the Fermi energy is a constant. So also is the Fermi vector, is a Fermi vector. So what it implies is that we have generated extra states below kf to accommodate extra electrons. It may be either positive or negative because it depends upon what impurity you have doped. For example, let me consider the case of copper, dope aluminum in copper, then we have one extra electron. So if we have one extra electron, sorry, not aluminum, zinc. So if we have one extra electron, then the impurity should generate an extra state to accommodate that. That is because you must have the constant Fermi energy, accommodate that below the Fermi level. So for each angular momentum L, so for each L we generate delta kf minus delta 0 divided by pi, and for each L we have 2L plus 1 degeneracy. Because we are not considering a magnetic impurity, and so the all the M levels corresponding to a given L are degenerate. Having given that, so what we have is total number of states generated is equal to sigma over L 2L plus 1 times delta kf minus delta 0 divided by pi, and then every state will have 2 energy levels. So I can actually put 2 there, and this is summed over L, and so this is the extra number, okay, and delta 0 we can take it as 0, because the wavelength of a k equal to 0 wave is infinity. So, the phase shift can be simply taken as 0 because it is not it has infinite wavelength. So, once we do that, then the total number of states generated is equal to 2 by pi sigma over L 2L plus 1 into delta Kf, which is L. Okay, delta depends upon L, the angular momentum. So, what we have is, what the Friedel sum rule says is that this should be equal to the number of extra electrons in the system. This should be equal to Z, the number of electrons added or removed from the system. So, we have Z is equal to 2 by pi sigma over L 2L plus 1 delta L Kf is known as the Friedel sum rule. What one usually does is that you have a screen potential. So, usually we have screened potentials due to impurity, that is, impurity potential is screened. Let us assume the screening parameter is lambda. Then we can actually fix lambda in an interesting way. Then we can choose a lambda, then calculate phase shifts and check if it satisfies the sum rule. The lambda that satisfies the sum rule, that satisfies that yields, let me call it, that yields phase shifts which satisfies the sum rule, is the screening constant. So, you see, we can easily fix what the screening constant for the potential is by calculating the phase shifts and using the Friedel sum rule. What I will do in the next lecture is continue from here and show you that Friedel's analysis actually gives you a charge density which is oscillating at large distances as cosine 2 kf r by r cubed, and this is something that I will derive in the next lecture, and those oscillations are known as Friedel oscillations and have indeed been observed. So, we will meet again next week to discuss further. Thank you.